Hello everybody, this is Thomas Strauss from BlueSky Energy. I'm happy that you found the time to join us today for another GreenRock session. Today we are going to cover the topic of dimensioning of storage systems. Starting on some basics about our webinar. Again, on the right hand side you've got the checked functionality. You can maybe use it right now. If you can hear me properly, just give me a short feedback, that would be great. And as always, if you have got some questions, please let me know and I will be happy to address those questions. All good. Thanks for your feedback. So I'm happy that you can hear me properly. I'm Thomas Strauss. I'm Managing Director of BlueSky Energy, and I'm happy to guide you through the dimensioning discussion today. The whole topic is starting off basically with some terminology. What we will go and discuss first is the degree of self-consumption or direct consumption. What is that? Then the degree of energy autarky, which we'll address. And then also talking about how can we optimize the potential of PV or maybe also wind energy, what we are going to generate, and how can we optimize that besides, of course, storage. And the second part will go into more topics of dimensioning, the photovoltaic and the storage system. Dimensioning the own consumption, direct consumption topic, and then basically going into the area, how big should a storage system be, considering all those factors. That, as you can see over here, is a classic curve of a household. We see shallow consumptions in the night, starting from midnight. Shallow consumption, that is basically the fridge, could be some heating elements. The jumping consumptions in the morning when the house gets awake, when the people get up, when they throw on their coffee machines and toasters. We see that spike over here in terms of consumption. Then it goes down again. Persons are going to leave the house. And then we see, in this case, a drop at noon, and then we see a big spike again around 6-ish in this case. That will be probably the time when the people are coming back from work and going back home. So that would be probably a profile which is a common profile, and probably it's a working day profile. So, and as we all know, the problem what we have now is that we have got, in this case, photovoltaic or solar energy, and the solar energy is starting in the morning, is getting up to the peak at noon, and then is going down towards the evening again. So it's a classical bell-shaped photovoltaics return topic. And of course, as we can see, we've got a mismatch. We've got the need for energy in the morning and at night, and we have got the energy during the day. And we can see the mismatch over here, that there is a gap. That's the white part of there. Of course, the green part is serviced directly from the photovoltaic, which is great. And then we have got one part over there, which is basically a topic where we need to look into properly. Without having storage, without having special tools, we either need to feed that energy back into the grid if it's allowed, or we need to cut down on PV production in order to match the PV production with the real consumption. So far so good. I think not much also new for you guys. So basically, what is then the self-consumption? Self-consumption or the direct consumption is basically that part of energy used directly from PV production. And in our graph, we can see the green part is the direct consumption. The yellow part is either feedback or lost, and the blue part is not covered. And the goal, of course, should be to optimize that situation and get some flexibility into the whole system. And the formula basically is, and I do not want to bore you all too much with formulas over here, it's basically how much of the PV is directly consumed in relation to the total PV production. And you can see then that's the self-consumption share, basically by PV direct or photovoltaic direct consumption in relation to total photovoltaic production. Again, just putting it with a couple of numbers, assuming that the total PV production is 5,250 kilowatt hours, we can obtain that data from the PV inverter. We have got a grid feedback from your energy bill of 3,750 kilowatts. That gives us 5,250 produced by the PV minus 3,750 kilowatts, which is fed back into the grid. So the difference are the 1,500 kilowatt hours, which are consumed directly, and that in relation to the total PV production is 30%. So in that case, in that scenario, we've got a self-consumption, a direct consumption of 30%, and the rest in this case is fed back into the grid. And the difference now in terms of self-consumption in relation to autarky or self-sufficiency, that's basically the degree what we are really producing ourselves and where we are not reliant on external sources like the grid. That's basically the autarky, which of course is certainly something from an emotional perspective. How much do I get independent of the grid? How much can I sustain by myself without need of external energy sources? And the self-sufficiency or autarky, it's basically the red part. That's the stuff what is needed to be sourced from the grid and not part of the autarky topic. Of course, it's always then the green part, which is the stuff which is self-consumed in relation to the part which has to be obtained or purchased from the grid. So the PV direct towards the total consumption, as I said. And as I said, I do not want to bore you all too much with the formulas over here. I think it's clear that's basically the topic in relation what's really what we need to buy and how much can we be independent from the grid. So that would be one example over here. We still have got the 1,500 kilowatt hours. That is from the example beforehand. We've got the total consumption. The total consumption is 4,500. That is the 1,500 which we are consuming directly from the PV, and the 3,000 which we need to source from the grid. In this case, our autarky degree is 31%, or self-sufficiency degree is 31%. And our goal is then, of course, to understand how can we improve that situation and how can we do that. Of course, we can add storage. That is our business. That is our core business over here. And the second part, of course, would be to using other tools, which I will outline shortly. So our goal is, on the one hand side, to bring that excess purple area either in front of it or in the back of it. And one tool, of course, is that's the storage part. We are storing the purple excess PV energy into the battery and provide with that then the energy consumption needed at night and in the morning. That is our classic business, and how we can optimize with the battery the overall self-consumption and of course also the autarky of the system. On the other hand side, of course, there's also the option that we are doing some load shifting. When we've got a load over here and it's a flexible load, maybe there's a chance that this load is not occurring at the time when we've got no PV energy, but maybe we get a chance to shift it in an area where we have got excess energy in order to match energy production and demand. And of course, the combination then, that's the golden goal of the whole thing, that we can start shifting the energy demand into the area where we produce the energy, and the excess is running into the battery, providing then the rest of the energy when it's needed. And that's basically the GreenRock storage, the battery part of it, along with the GreenRock EMS, that's the energy management part of it, which enables us to shift the loads to a certain degree from times where there's no PV energy to times where there is PV energy. So how is that done? For example, we have got our example number 1. That would be a dishwasher. Normally, in most households, we've got the situation that in the morning, the dishwasher gets loaded and then everybody leaves the house. And the washing machine is then basically turned on. So we've got the energy consumption in the morning, but the sun is not up and we've got no PV energy. So a very easy way to do is always, of course, if the houseman or housewife in charge of the washing machine is permitting it, is that we are using wireless sockets. How does that work? The wireless socket is basically put onto the normal socket where the washing machine is plugged on. In the morning, you are filling the washing machine, you're putting in your powder and set everything to start, but the washing machine is not starting yet because the washing machine has got no power. That's the smart plug. Once the sun is coming up, that's the area over here, the smart plug with the EMS detects, oh, I've got excess photovoltaic energy now, and gives the signal to the smart plug and says, look, washing machine, start, go ahead. And then the washing machine starts at the time when the PV is up and running and is, of course, providing the energy. In this case, we are shifting energy from the morning into an area where we have got excess energy, and therefore flattening out our energy demand and supply. And of course, the smart plugs and the EMS can do a little bit more than that. What is if we have got a cloudy day and we have got no excess PV at all during the day? Of course, then we can implement a certain mechanism that we say, look, if we are having energy until 1 o'clock, then smart plugs should start when there's excess PV. But if this is not the case, start ahead nevertheless, because we want to have our garments washed by the end of the day. The second example over here is a dishwasher. It's a flexible consumer which could be used also in that direction. Instead of switching it on in the morning, we can tell it with the spark plug, start ahead once the PV is available and start ahead. So that would be that we are shifting also that demand over there, and normally maybe the dishwasher is running at night or in the morning, so we're shifting that load into the PV area where we've got excess PV. The number 3, that is our classic example, that we are taking then the excess of that energy, the normal energy what we have, that's the green curve, along with the additional energy need consumed by the washing machine and the dishwasher. There's still some excess energy, and that excess energy is then pushed into the battery. That's the orange part over here, and is providing then our energy supply at night and in the morning. That's our classical energy storage business, that we are shifting excess energy into areas where it's needed. Then you can watch TV or make cooking with your battery. And one other example would be, for example, the e-charging part of it. The e-charging part of it, when you are getting home, that you are then using the e-charging with your excess PV. Only would be charged at night, but then we can shift it a little bit earlier, of course, permitting that the car is back home. So all those measures in combination enable us to optimize the self-consumption and in consequence also the autarky of the PV system. And of course, in our case, it's also possible to start off with the EMS only and add the storage later, or start with storage and then enlarge your capabilities with the EMS. We are flexible. And of course, each deployment, each customer will be different. Those examples are examples from a residential area. Of course, there are also commercial deployments. And especially in the agricultural area or segment, there are also big consumers like pumpings or heatings or venting machines, which do not necessarily always need to run at a specific certain time. We've got some flexibility there, and that flexibility enables us to shift the load into the area where we've got excess energy. Another fabulous example would be also maybe for tourism applications or bigger homes. If there is a pool available there, for example, the pool pumping is one example. Also, the pool heating could be examples where said, yeah, we need to do something at some point during the day. The pool needs to be pumped and cleaned, but we want the pool that it's then pumped and cleaned and energy consumed once there is an excess energy. So that's how we work on that end. Any questions on that end? That's the combination of the EMS and the storage, which of course is an integrated part of our GreenRock storage solutions. So the EMS is always one part which comes as integrated part within our systems. So how does the whole thing work? I mentioned already from the EMS part, we've got the remote or radio sockets. We can also say smart plugs for that, for washing machines and dishwashers. I just outlined that example already. We can integrate the e-charging for mobility, which is power controlled. One other option, of course, what we have is that we are integrating heating elements and make power to heat topics. Before we have got excess PV, which triggers us that we have to curb the PV production. We are taking that excess energy, and with the heating element, we are heating up the boiler. For example, the boiler is at 60 degrees Celsius, the water temperature. We've got excess energy, and then it's configured. Then once there is excess energy, we are putting that energy into the heating element and therefore heating up the hot water up to 80 degrees centigrade. And then we can use that energy effectively with hot water for showering or cleaning or whatever. Another option is, of course, that we integrating the EMS into heat pumping system. That could be the air pumping topics or the ground pumping topics, that basically we are using the excess energy to push up the heat pumping activity and use then the warmth of the heat pump. And as I also outlined, all variable consumers are options for us to optimize the self-consumption. And we can integrate that with multiple energy sources. I use here the example of photovoltaics, but of course it's also applicable if we have got wind as a source, or we've got diesel generators as a source. We are not bothered, or even if you've got multiple sources like wind, PV, diesel, and the grid, we can handle that. And the goal is for us that we are matching basically the energy consumption with the energy supply, in order to smooth that out. And our experience is that self-consumption of bigger than 90% can easily be achieved with those activities. In general, in terms of sizing of systems. I'm talking about photovoltaic sizing, and I'm not going into deep there because you might be much more equipped to address those topics. Of course, the PV system should match in terms of consumption in respect to the production, in terms of the consumption what we are having in the house. And of course, if the PV system is too small to support the local energy demand, there is little possibility for the battery or the EMS to optimize that. And if you are dimensioning photovoltaic system, also future demands should be taken into account, and that would be, for example, e-mobility factors. So how much should a photovoltaic be? I'm taking an example here that is an Austrian or German example. And in Austria or Germany, we are talking about 4,500 to 5,000 kilowatt hours per year. That is an annual consumption of a typical normal household. And we are assuming that we are getting out of 1 kilowatt peak photovoltaic or solar about 1,000 kilowatt hours in annual energy. So the consequence would be that we have got in average 5 kilowatt power peaks photovoltaic or solar system for common houses over here. Of course, taking into account the future energy increases, of course, what we are seeing, more and more energy intensive gadgets available. So there could well be that we are saying, look, let's increase the photovoltaic to a certain degree, make it a little bigger, times factor 1.2, 1.5, to cater that energy also for the future demand, which might be coming along in the near future. Maybe e-mobility, maybe it's more electronic equipment needed. So also from the photovoltaic side, we should, of course, consider what's the peaks which are measured. And of course, it should also be considered the shading factors. And again, you know that better. And we have got, for example, with that link from the photovoltaic geographical information system, there's a good overview how much kilowatt hours you're getting out of your kilowatt peaks. That's just information, but of course, there are also other tools available which help you to dimension those systems. That is just an example of that photovoltaic geographical information system where you basically put in your location. In this case, I put in the Austrian location of our site, and you're obtaining then the information, how much kilowatt hours and how much stuff you're getting. You can also select the roof angles and the consequences out of that. And then you're getting the data that's pulled out of that photovoltaic system, as I just mentioned. And then we've got the distribution by month. We see in January, February, as well as November, December, a rather shallow energy production. And we've got the peak starting from April until August. That's a typical curve, what we are seeing in Northern Europe. But of course, might be different for your countries. But you probably know that better than I do. So how do we get the information from the energy consumptions? And that is always a little bit the tricky part when we are coming to a new customer and said, look, how big should the photovoltaic be? How big should the consumption be? So of course, the one easy way to obtain it would be the energy bill, that we're seeing the energy consumption on an annual basis. That, of course, does not really give us any distribution throughout the year or days, but it gives us a first rough guideline. The second way and the best way would be, of course, to get a load profile of selected dates, having a working day in January, having a weekend day in January, having a working day in April, having a working day in July. And that, of course, gives us a very strong load profile and very good information how the load in that house is distributed. That is the best way to obtain consumption information needed for dimensioning, storage, and photovoltaic. And of course, there would be a manual way if we engage the customer and say, let's do a counter checking, that's the manual part, and check your counter and write it down. What's the energy, accumulated energy at 7 o'clock, at 12 o'clock, at 5 o'clock in the afternoon, and therefore obtaining the profile, how much energy is consumed in certain time frames. So that's basically how we can derive the energy consumption in a house or industrial application. The consumption is always, of course, then depending on the consumer behavior. Are there kids around? Is it a working couple? When do they cook? Do they cook at all? Do they dine out? When they're using the washing machine? So that's basically the distribution throughout the day, and maybe also deviating then through the weekdays and the weekends. Do they have got the heating system? Is that an electrical heating system? Or do they have got any other source of heating? And do they have got e-mobility? All those factors are one of the main factors to be considered when we are looking into the consumption distribution during the day or during a week. And the other part, of course, is how much is the PV generated. Of course, the summary basically of the data, what we need is then the PV data, how much PV energy is generated or calculated, how much is the energy consumption, maybe from the energy bill. And of course, then there are different details like kilowatt power installed and the alignment of the room, which give us all the data needed in order to understand how much energy will be produced by the alternative energy sources and how much energy is going to be consumed in that specific application. So that was the basic consumption of our example, what we had beforehand. We had an annual PV production of 5,250 kilowatt hours. We had 30% self-consumption. So the surplus was 3,675 kilowatt hours. That was the very, very basic information what we had from that system. So we are saying that in terms of how to dimension the storage system without factoring in EMS effects like load shifting. So the average storage system in that case should be 10 kilowatt hours. So again, we have got an annual PV production of 5,250 kilowatt hours. We determined 30% out of that is self-consumption. So we've got a surplus of 3,675 kilowatt hours. And the consequence is 10 kilowatt hours per day. And of course, you might raise your hand and say, look, this cannot work. You showed us there is not much production in January and November, and there is more production in April and August. And that is true. And in this case, we always take that average, because what we see is that in November and January, we are about half of that production. And in April and August, we have got about double of the production. And that is basically where our EMS facility kicks in to level that out. So we are taking the average in a Northern European application. Of course, that will be different if we are talking about other countries where we have got a better distributed sunshine environment throughout the year. And talking about the autarky, we have got about 8.5 kilowatt hours per day, which we are sourcing from that grid in that specific example without adding any battery or EMS. So when you are approaching projects, and that is my experience as well, very often you do not have all the data available, and but the customer wants some price information upfront. And of course, it's important to start and enter the game before the customer is having the data ready. So in general, what we say is, as a rule of thumb, the storage capacity should be matching the KVP performance of the photovoltaics. So if we have got a 5 kilowatt peak photovoltaic system, we are recommending a 5 kilowatt hour storage system, or 1.5. So in that range we are working. So that range would be our normal recommendation for a first pitch, for a first calculation. If you have got 5 kilowatt peak of photovoltaic, we are recommending that the storage should be 5 kilowatt hours to 7.5 kilowatt hours in recommended capacity. And that would be the starting point, enabling you, giving you a first quote out to your customers, and using that as a basis for further discussion and getting the project started. Of course, when you dimension the storage system, as I outlined already, we need to consider the production side and the consumption side. It's photovoltaics in that example. It could be wind, it could be diesel, it could be something else. If you've got a large PV and a small consumption, storage is always fully charged, but not always fully used. The consequence in that case, if you have got a too big of a photovoltaic system, there's a very long amortization time for the investment. And on the other hand side, if the PV is too small, we have got a relatively high consumption, self-consumption, and there is a little impact on the self-sufficiency. So it's important from a cost perspective, from the investment perspective for the customer, that we are getting the sizing right. And therefore, we are recommending the 1-to-1 or 1-to-1.5 rule as a starting game for dimensioning storage systems. Over here, I'll show you a couple of data points from our EMS. By the way, the EMS, the GreenRock Energy Management System, will be addressed in more detail within our next webinar. And then we can see the data very clearly. We can see the yellow parts of that cake, that 30%. That is the self-consumption quota from GreenRock system. This is real field data, what we have. And we see is 30%, over here 35%, 28%, 30%. So that's basically really one rule of thumb over here, which we can see. Then this 56%, the blue part that's the excess energy which is going into the battery. So over there is 56, 61, 38, and 32. That is getting into the battery. And of course, as we can see, the rest is then what's getting back into the grid. So what we can tell from that data is, over here we have got a rather big storage, and over here the storage is a little bit too small, because 38% run into the storage and 31% run back into the grid. Over here, even 40% run into the grid. On the other hand, over here, 61% run into the battery, and only 4% remain then for the grid. So you can see how the dimensioning varies for different applications. And the good thing is, with that EMS, the customer can see the data, but you as an installer can also see in the portal all your installations with one glance and understand where the self-consumption and the whole overall system is. And that, of course, gives you as an installer also the opportunity doing some upselling then. Because with that data, you can come back to the customer and say, look, I had a look at your system, and you are putting way too much energy back into the grid. Let's discuss how can we optimize that. Maybe we should work with EMS functionalities to optimize that, to load shift it, or maybe we should think of enlarging your storage. And so we can help the customer optimizing the PV or they are. Over here, another example. This is also showing similar data, and this is also again data from our systems. So it gives you a very good overview, and of course you can then drill down different days, different months, all the data is there, and it should be a tool to give the customer a good view where they stand in terms of self-consumption and autarky, and you get a feel if the dimensioning is right. And of course, for you, it should give you an opportunity improving the situation for your customer and hopefully also generating some business out of it. So with the correct dimensioning of systems, we experienced that we can increase the self-consumption quota of 60% to 65%. So we can substantially increase the self-consumption quota, and we can also increase the autarky from 55 or 65% towards the customer. And with GreenRock EMS, self-consumption can be increased up to 90%, and the autarky can be increased up to 70%. So it's a very powerful mixture what we have. Storage on the one hand side, where we are shifting the excess energy into areas where it's needed, and doing the load shifting with our EMS to bring the needed load into the areas where we have got the energy. I outlined that it's hot water, smart plugs, and so forth. I do not want to elaborate again on that. And of course, if the customer is a little bit hesitant, they have got a photovoltaic installed, or they are thinking of installing the photovoltaic, there could be one first step, and there will be a low investment step, starting with GreenRock EMS first. Investment is around, let's say, 1,000 to 2,000 euro. We can start increasing the self-consumption, and the good thing would be that you as an installer and the customer can obtain all the data needed for doing then the right dimensioning of the storage system in a second. To point your focus to, there will be a gradual getting into the storage business, starting via low investment EMS first. Therefore, we are seeing all the data, everything is transparent. We can optimize some stuff with smart plugs or hot water or e-charging. And as a second step, when we are seeing the load profile out of the EMS then over 1 year or 2 years, we can come back to that customer and say, look, we have got the data already. The optimal storage size for you would be 7.5 kilowatt hours. So that is one step to be considered and might be one route to sell into, let's say, more investment reverse customers. Okie dokie, so far to the topic of dimensioning storage systems. If you've got any questions, please address them now. What I didn't elaborate on very specifically is off-grid applications. So how much should be the storage for off-grid applications? And that is really depending on how long does the customer want to be self-sufficient, how long should that be? And it would be basically what's the daily consumption in relation to what's the daily production. And then we need to assume that production is failing because we have got bad weather. And then we are taking the daily consumption and then multiplying the days, how long the system should sustain basically the system. Okay, I've got a question here. Do you have a calculation for transmission loss from battery source to usage side? Do you mean the round trip efficiency of the battery? the round trip efficiency of the whole system that compromises the battery itself has got a round trip efficiency of around 88%. So if we are putting 100 in, we are getting 88 out of it. So that's the round trip efficiency of the battery itself. And then we need to consider the battery inverters and cabling and everything. And our experience is that the round trip efficiency lays at about 80%. Okay, so as there seem to be no further questions, I just wanted to draw your attention very quickly onto the final webinar, what we're having in this autumn round, that is the GreenRock EMS. I explained basically what are the benefits of the EMS and how smart plugs and all that stuff is going to affect positively. In the next, we would probably go more into detail, how it's deployed, how it's looked on, how it looks like, and what can be done additionally with that EMS, because it's a very powerful tool. Okay, as always, we will provide that presentation, and for all those who missed the last presentations, they are all available on our YouTube channel, and I will make sure that in the email sent out to you, we will enclose the link to the YouTube channel, that you've got the chance to also watch the last presentations what we held on that topic. I thank you very much. It was a pleasure again having you. I wish you a great day and hope to see you next time. Thanks a lot. Ciao, bye-bye. Thank you. Ciao, bye-bye.